All right, so let's talk about actually using this normal distribution. So in our example, when we first did the problem, we had the statistics test with a standard deviation of 10 and a mean of 75, and we put that on the standard normal curve. Okay, sometimes we're going to be looking up values that are not like easy to find. They're going to be like 1.47 instead of 1.5, things like that. So to do that, you can use this formula to find those values that they correlate to. And this formula is z is going to equal x, so the value that you're going to look up, minus the mean over the standard deviation. That will standardize any score, meaning that will put any x value onto the standard normal curve. Remember, the standard normal curve is that curve with a mean of 0 and a standard deviation of 1. Okay, so if I look at these examples, I have the Wechsler Adult Intelligence Scale, an IQ test that's been in use since 1955. The scores are known to be normally distributed with a mean of 100 and a standard deviation of 15. Determine the probability that a randomly selected IQ test score is less than 108. Okay, so there, when you say, okay, well, the standard deviation is 15, 108, that's going to be between 100 and 115. Okay, so if I'm looking at this and I'm trying to standardize these scores, okay, here's 100, here's 115, it's going to be somewhere in between there. So you want to find that exact value. So you're going to use the formula, z equals x minus the mean. So in this case, the x is going to be 108. The mean is 100. And then we're going to divide by the standard deviation, which is 15. So that would give us 8 over 15, which is 0.5333. So we'll do 4 decimal places. Okay, so if I'm looking at this scale down here, that's about right here. So that's where the 108 is, which means on the standard curve, it's right here, 0.5333. I want the probability that a test score is less than that. So if I take this and I look at the curve, I am looking for the area less than that, so the area to the left. Okay, so on my calculator, I can put the command in for normal CDF, -99, and then 0.5333. So second distribution, normal CDF, -99 for my lower limit, my upper limit, 0.5333. So that's going to give me 0.7031. So the probability that a randomly selected IQ test score is less than 108 is 0.7031. That's going to represent this area right here. Okay, or I could have looked that up on the table as well. Now another thing, we'll look at the next example. So now determine the probability that a randomly selected IQ test score is greater than 97. Okay, so greater than 97, so if I'm looking at this, that's probably, here's 100, it's going to be close to 0, just a little bit below 0. But you would find the z-score, go 97 minus 100 over 15. Remember, 100 is the mean, 15 is the standard deviation. So that gives you -3 over 15, which is -1/5, so I think that's -0.2. Yeah, negative 0.2. So that is looking up right about here on my curve. And then I want that it is greater than that value. So I want it to go to the right. So slightly over 50% since it's right next to 0. Okay, so let's look at that. So I'm going to go normal CDF. My lower limit will be negative 0.2. My upper limit, positive 99. And that will give me 0.42. I don't think I put that in right. I did not put that in right. Negative 0.2. Negative 0.2. There we go. 0.5793. 0.5793. Now, some of you might notice that you do put the mean and standard deviation on the 84 calculator. So I could technically come here and go, leaving my values here, a lower limit of 97 for my value, my upper limit of 90, this would have to be like that, a mean of 100, and a standard deviation of 15, and it will do it for you, the same thing on the calculator, so you don't have to find the z-score, but only if you're given a problem like that. You are going to be given problems that are going to be multi-part, or it's going to be what is the z-score, and then determine the probability. So it's easier just to keep it on the standardized with finding the z-score first, and then finding the probability. So keeping it at 0 and 1. Okay, but you can technically skip this step if the problem is solely asking for the probability. Determine the probability that a randomly selected IQ test score is between 95 and 110. So then if it's between two values, what we would want to do is find the z-score for both values. Okay, so you would start with the 95, the lower value. You would go z-score. It would be 95 minus the mean of 100 over 15. So negative 5 over 15, I think that's negative 1/3. So negative 0.3333. So that's this first value, so probably about right here. And then the second value is 110, so 110 minus 100 over 15. So I think that's 0.6667. Yeah, so 0.6667. So about right here. So we're looking at this little margin sliver right here. It looks to me that's about 30%. Okay, but if we want to look this up, again, we could look this up in the z-table, look up both of these and then subtract. Okay, or go normal CDF. Your lower limit would be negative 0.3333. Your upper limit, 0.6667. So second distribution, normal CDF, negative 0.3333, and then 0.6667, with a mean of 0 and a standard deviation of 1. And that's going to give us 0.3781. Okay, so the probability that a randomly selected IQ test score is between 95 and 110 is 0.3781. All right, so we have one more question and then some practice, which I'll let you guys do on your own. But let me see here. Okay, so let's do another example here. So the weights of full-term newborn babies are known to be normally distributed with a mean of 7 pounds. So our mean is 7. And a standard deviation of 1.5 pounds. So determine the probability that a randomly selected full-term baby weighs between 5.1 and 10.1 pounds. Okay, so here we would then standardize both of these scores. So we would go Z, start with the 5.1. So 5.1 minus 7 over 1.5. So that is going to give us 5.1 minus 7 over 1.5. So negative 1.2667 for our first z-score. Okay, then our upper z-score, so let me just put this on here. So about right here. Then 10.1 pounds, we would go a z-score here. 10.1 minus 7 over 1.5. And that's going to give us 2.0667. Okay, so on the curve, this looks like about this. So we're going to look for this area right here in purple. Now to me, that looks like that's probably about 80%. Okay, but we want to find the exact values, so we will either look up both of those tables, both of those in the Z table, or we will go normal CDF. We'll have a lower limit of negative 1.2667 and an upper limit of 2.0667. And let's see here. And that'll give us 0.8780 when I round that. Okay, then the next one, determine the probability that a randomly selected full-term newborn baby weighs more than 5.75 pounds. So this would be greater than 5.75, so 5.75 would be our x. Subtract that from 7. Divide by 1.5. So 5.75 minus 7. Divided by 1.5 is going to give us negative 0.8333. Okay, which on this curve, that's going to look like about right here. And we are going more than, so that's going to be to the right. So this should be slightly over 50%. Okay, so in my calculator here, I would go normal CDF. My lower limit would be negative 0.8333. My upper limit, 99. And that's going to give me 0.7977. Okay, again, that's the probability that a randomly selected full-term baby weighs more than 5.75 pounds. That represents this area here, shaded in purple. And then determine the probability that a randomly selected full-term baby weighs less than 9.2 pounds. So let's find the z-score for that. 9.2 minus 7 over 1.5. So that would be 2.2 divided by 1.5. So that gives us a z-score of 1.4667. So that's about right here. And we want the probability the baby weighs less than that, so we're going to the left. So we're looking for this area shaded here. So we would go normal CDF. Since we're going indefinitely to the left, our lower limit is negative 99, and then our upper limit is 1.4667. So negative 99, 1.4667. And that's going to give you 0.9288. And again, that represents this area right here. And that's the probability that a randomly selected baby is going to be more than 9.2 pounds. Sorry, less than 9.2 pounds.